Hi, we are team number 7, and we're going to go through problem number 6.6-1 in your operations research textbook. The problem that it gives us is a maximized Z problem that can be solved using a Tableau or WinQSB. Because you have basic linear programming knowledge, we're not going to take you through all those steps because we want to get to the more exciting stuff. But the solution, as you can see from these two constraints, is going to be that x1, x2, and x3 are 5/3, 0, and 3 respectively. Now if you come over here to the tables I have set up top, all that I did was take the original form. As you can see, this is what we were just looking at. Here's your maximized Z problem here. Our right-hand side, these are our inequalities, and these are our variable coefficients. Now, what I wanted to show you is how the original problem, or as we like to call it, the primal problem, translates into a dual problem. You can see the green letters that I put here, which are our current right-hand side, actually translate into our Z coefficients that you'll see over here in the dual solution. And also, the other thing that will change is your variable coefficients start like this and then pretty much just flip over on their side, and you can lay them out this way. So when you actually plug them in and want to put them into the problem form, we can scroll down here, and you can see I have that table displayed more neatly, where you have your negative Z, because this is a minimized problem now, is equal to the 25 plus 20 that we actually saw on the inequality sides of the original problem. I also listed the original problem here so you can really see them directly pulled from the original restrictions, the original constraints. They are literally just pulled and put up into your minimized Z problem. And then these are your subject to, these are your new constraints. They actually were derived from your original constraints, just flipped on their side. Now you're going to go over and go with Ty to figure out how we find the optimal for this problem.
Alright, basically the graphical method is the easiest way to do this. So from Maggie's information there, we are able to find our equations. We set them equal to 1 instead of greater or equal. And so we got our first equation down here, second equation here, and our third one here. Now it's a minimized problem, so the feasible region is going to be out here. So you pretty much want to find this point right here, which is the optimal solution, which is the lowest possible point you can get. And to find that point, you are going to use the substitution method for each of these two equations. And when we do that, we get 1/5 for y1 and 3/5 for y2, and which gives us a z-score of 17. Now we'll go over to Zach, and he'll show us a little bit more.
Alright, so if the problem gets changed to, it's the same problem as you can see it, the values that are changed are highlighted here. Well, what happens is when you flip it over, it only can change the one constraint. As you can see, it's been rewritten here. So, taking our answer from the other problem, we test it to make sure it still works. We take our y1 of 1/5 and our y2 of 3/5, plug them in, and we find that we get 2.2, which is definitely not greater than or equal to 3, so it's been violated and it is no longer an optimal solution for this problem, this new problem. Now we're going to go over here and look at problem part F.
Alright, in part F we add another variable which we call x new. Now we're going to test and see if the optimal solution is still feasible after we add this solution, or this new variable. So we got same maximization with the new variable, subject to these constraints, the 3x new and the 2x new respectively, and as usual, greater than or equal to 0. Now we'll head over to Maggie's chart from earlier, where she has added the x new variable into her table here. So this will give us our equation, the 3y1 and the 2y2 is greater than or equal to 2. Now we can put that on our graphical method from earlier, which is this black line right here, part F, and we see that is the old optimal solution is less than this new constraint, which means it is not acceptable and will not work. And that is all.
Thanks for watching.